So I'm Nathan McNew. I'm a graduate student in the math department. Fifth year. I'm graduating this year. And my research is in number theory, specifically combinatorial number theory. So I'm interested in counting sets of integers, asking how large is a set of integers, or asking how large does a set of integers have to be before it's forced to have some property.
I work in the Ramanathan lab at Dartmouth, where we study the microscopic world of electrons and nuclei. And the way we probe what's going on in their world is using a technique called nuclear magnetic resonance, or NMR. But there's a really big problem with this technique in that it's extremely insensitive, sometimes to the point where it really limits the applicability of what you can study with it. What we're trying to do is come up with ways that we can improve the sensitivity of nuclear magnetic resonance so that we can study really, really interesting samples, such as 2D surfaces or thin films.
In the Bickle lab, we study what makes a woman's biological clock tick. When I refer to the biological clock, I'm talking about the phenomenon that during a woman's 30s, her chance of having a miscarriage or a child with birth defects increases exponentially. This is usually caused by an error during the cell division that creates the egg, whereby the egg receives the incorrect number of chromosomes. In our lab, we're interested in the steps that go awry during this process. Previous work suggests that it's actually the protein linkages between the chromosomes that are deteriorating with age. However, the mechanism for this deterioration is unknown, and that's where my research comes in. I use this fruit fly, Drosophila, to study what could possibly cause the deterioration of these protein linkages. Specifically, I'm looking at oxidative chemicals that are natural byproducts of the cell that are known to damage the cell with age. I manipulate the levels of these chemicals in the ovaries of the fruit flies and measure the impact on chromosome segregation.
Recently presented a poster on quantitative analysis of Supreme Court writing style as part of my PhD thesis, hopefully eventually, for the computer science department here at Dartmouth. So we started out this with a corpus of every Supreme Court opinion ever written. This is about 25,000 documents dating back to the 1790s. We wanted to look at the way that the style of writing has changed during this time. So we look at the way that different justices use different content-free words, which are prepositions, articles, and these types of things, and the frequency with which they use those. And we found that time periods have very definite stylistic signals. So two justices writing in 1800 will write a lot more similarly to one another than a justice writing in 1800 and one writing in 1900. So this was an interesting find, but the real result was that we looked at what happened once Supreme Court justices started to use clerks for their opinions. So a lot of Supreme Court opinions are no longer written by the justices themselves anymore, but they're passed off to peons. They pawn it off on somebody else to write the actual opinion for them. And so we saw evidence of this in our stylistic analysis. The modern court has less consistency in their style because we assume, are no longer actually writing the opinions themselves. It's actually a team of people writing those opinions. So our conclusion was that based on this stylistic analysis, we think that not only are the Supreme Court justices making use of these clerks, but that the trend is that they are increasingly relying on these clerks to write their opinions.
I work on a new imaging technique called magnetic resonance elastography, or MRE for short. The main goal of MRE is to produce or to calculate mechanical properties of whatever tissue that you're looking at. And when I say mechanical properties, we're looking at things like stiffness or permeability or fluid flow characteristics of that particular tissue. If we look at, for example, breast cancer, we know that the breast tumor is a lot more stiffer compared to the rest of the breast tissue. So if we looked at an MRE scan of it, you would see that you have high values of stiffness compared to the rest of the tissue, and you can localize your tumor to that region. So currently I'm working on brain tumor data sets and looking at the varying levels of stiffness between patients that have different types of brain tumors.